Okay, hi there. This presentation is about building a calibration for the Drainac 3B online freeness analyzer. Okay, let's start with this. What the Drainac does is measure time. It basically measures how much time it takes for your stock filtrate to fill the volume between the two analysis probes. And it looks something like this. So you can see that it takes X seconds for your stock to fill the volume between the two analysis probes. That is the native measurement of the Drainac. It's called cycle time, or in its filtered version, the drain time. Uh, what we need to do is, in order to build a calibration, we need to understand the relationship between the Drainac time measurement and your stock freeness. So every stock has its own relationship. A particular time measurement is going to relate to a specific freeness value. X seconds is going to correlate to Y freeness. And of course, what we have to do is find out what that relationship is for your stock, because every stock is a little bit different. And the means by which we do that is by actually building the calibration. Now, when it comes to calibrating a Drainac, there are basically three approaches. There's the so-called best fit line approach, which is my recommended approach. There is the built-in routine called AutoCal, and there's a second built-in routine which is called LabCal. We're going to cover all three of these methods in this presentation today. So let's start with the best fit line approach. Basically, you start by collecting lab samples and plotting the Drainac cycle time versus the lab estimate of CSF. And here's an illustration of that. Once you've got that data, you basically calculate the best fit line to that data. And once you've got that best fit line, you just work with the line itself and not worry about the data for the time being. When you actually extract the equation for the line, and there are a couple of ways to do this. Some of the ways will actually generate some statistics associated with the regression. That's the 2 sigma that you've heard about, and we'll use that a little bit later in managing calibrations. Once you've got that equation, you've got a choice on where to put it. You can host it in your DCS. If you decide to do that, then you're basically finished with your calibration. You have your equation, you program your DCS and convert the 4 to 20 milliamp output of the Drainac into those units that you've developed. You're still going to want to pay attention to another section in this presentation called when to recalibrate rather. Your other alternative is to host that equation in the Drainac, and so that the Drainac outputs CSF lab values as opposed to drain time. In this approach, you've got a little bit more work to do, and we're going to go through that right now. So, hosting the calibration in the Drainac. The very first thing that we have to do is we have to basically choose the freeness range that we want the Drainac to measure. So we're going to specify some freeness of 0 and some freeness span to get two values, F1 and F2. Once we have those values, we see where those values basically cross the line, and we can then calculate the cycle times that are going to be associated with that freeness range. In this case, the T1 and the T2. Applying the parameters, the operational parameters to this graph, this is what we're looking at. So time 0 and span. And these are the values that you would then program into the Drainac. There are a couple of alternative methods of calibration. We have the AutoCal routine and we have the LabCal routine. So what's AutoCal? AutoCal is a built-in automatic routine in the Drainac, and it's designed, it's basically a quick single point calibration designed for relative indications of freeness. What it does is it takes 5 time samples and averages them together and then calculates a new time, zero, and span from those values so that you're roughly in the middle of your predefined freeness range. You see the numbers there that it'll actually use. Keep in mind that when you use one of these automatic routines like AutoCal or LabCal, it will displace the calibration that's in your Drainac. You'll have a brand new calibration that has probably very little to do with the calibration that was in there before. You don't want to use AutoCal if you want absolute measures of freeness. AutoCal is basically good for relative indications of freeness only. I'd like to kind of illustrate this point a little bit further. Here's an illustration of AutoCal. Here we have a system which has been calibrated. We have time ranges of running from 15 to 55 seconds, and freeness is running from 350 to 550 CSF. In this case, a measurement of 20 seconds will basically produce a freeness evaluation of 525 CSF. Now, if the Drainac is producing evaluations of 20 seconds at this point, that being what your stock is doing, and if someone were to hit AutoCal at that point, what would happen is this. You would get a redefinition of the calibration. The 350 to 550 wouldn't change anymore, but your time values would shift down to 7.2 to 47.2 seconds. So your 20 second analysis that was originally producing a CSF value of 525 is going to do something different. So now all of a sudden you have a value, 20 seconds are producing 486 CSF. So you had this big shift, and it's got nothing to do with your stock. It's got everything to do with the fact that the Drainac's been recalibrated. You basically have a brand new Drainac right now. Use AutoCal with care. You don't want to just push it willy-nilly. Okay. LabCal. So what's LabCal? LabCal is also a built-in automatic routine. This one's actually designed to be used for absolute measures of freeness. It's basically a very simple mathematical calibration where it takes 2 data points and then calculates the appropriate time, zero, and span for a particular predefined freeness range. My criticism of the LabCal methodology is that because it only uses 2 data points, it is not statistically robust. 2-point calibrations are almost guaranteed to have larger errors associated with them. If the better result is always achieved by going through the best fit line approach, which I went through earlier. But let's go through an illustration of what LabCal looks like. So we've predefined our freeness range, F1 and F2, and then we go out there and we basically have the system. We push the LabCal button and it'll capture 2 data points. All right, you'll capture hand samples at this time, and you'll provide the system with the lab evaluations associated with those 2 data points. So the system then will calculate a best fit line that runs between those 2 points, and then extrapolates the time values associated with that line. And so far, so good. The only problem is that those 2 data points really aren't going to be data points at all. They're going to have a lot of slop associated with them. And so the line that goes through those data points are probably not going to be the best fit. You can have a bunch of different lines going through those data points. Here are a few that are defined, and obviously the time, zero, and spans associated with those various lines can vary quite a bit. So when you use LabCal, you just got to keep in mind that what you've got is a quick and dirty indicator of freeness relative to your lab evaluations of freeness, and it is not the most statistically robust. Okay, there we go. So now you've calibrated the Drainac. You've done it in one of these ways, and the question is, when should you recalibrate? Well, if you went through a best fit regression, you'll have some statistics. I have another presentation on how to actually regress a best fit line using Microsoft Excel. You can use whatever package you're most comfortable with, but you'll basically develop some idea of the so-called 2 sigma. 2 sigma is a statistical measure which just basically means what is the average error of your data set that you use to derive your best fit line from the best fit line. The average error is called sigma. 2 sigma basically describes a variance in which 95% of the variation is expected to be within those 2 limits, or basically 19 out of 20 times you would expect your data points to be within those limits. And but that still means that 1 out of 20 times you would expect to see it outside those limits. So you wouldn't want to recalibrate if you saw that most of your data was within that 2 sigma variation. However, if you saw that the error consistently exceeded the 2 sigma limit, or if you saw that the error was consistently biased, typically always on one side of the line or the other, then you might want to consider recalibration. So let's take a look at some illustrations. Here's a situation where it's probably not necessary to recalibrate. There's our 2 sigma limits that we got from our regression associated with the best fit line. And here's some data points. And as you can see, most of the data points are actually within the 2 sigma limits. Yeah, there are a couple that are out, and that's okay. I wouldn't get excited about it. The statistics tell you that you expect 1 out of 20 data points will in fact fall outside of that region. If you get 1 or even a couple of more than that, I still wouldn't get excited about it until you started seeing a bunch of them all at once. So in this case, it's not necessary to recalibrate. In this case, however, you'll notice that most of the data points are actually falling outside of the regression 2 sigma. In this case, something's going on, and it might be something with the instrument, it might be something with your process, but it's time to take a longer look at what's going on. Maybe recalibration is called for. And here's an example where you probably would want to recalibrate. Here is a situation where you have data points. As you can see, they're all on one side of the line, and that's indicative that something else is going on. And again, we're not certain. This might be something that's going on with the Drainac instrument, or it might be something with the process. But in either case, it bears taking a closer look at. All right, so to summarize, the Drainac measures time. Every stock has a different time CSF relationship. We recommend that you use good statistical practices to develop a best fit relationship for your stock, and then use that best fit to program the Drainac either to host the calibration or to host it in your DCS. There are some built-in internal calibration routines. They all have limits and consequences. You need to be aware of that. Use the statistics that are derived from your best fit regressions to monitor basically the performance of the Drainac and make a decision as to whether or not recalibration is necessary as you go forward in time. All right, well, that's the show. Thanks very much for watching, and always please give us a call if you have any problems at 504-833-6381 or at sales@teco-inc.com. Thanks for your attention. Bye-bye now.